Hello, my name is Pablo Rivas, and today this talk is about a negative result that we think is very useful. The paper asks whether quantum rotation dropout can act as an adversarial defense in small quantum neural networks. The title gives away the core answer. It does not reliably defend. But the point is not that the project failed. The point is that a plausible quantum regularizers should not be trusted as a security mechanism until it is tested under the actual prediction rule and under an attacker that knows that rule. I will walk through the defense idea, the attack-aware protocol, and the main results. Transfer and four-qubit checks, and also the cost of doing the stochastic test correctly. The main message is that randomness alone is not robustness. For QML security, that's a valuable result. The security question begins with a tempting idea. If we randomly suppress trainable rotations in a quantum neural network, perhaps the classifier becomes less brittle. That idea makes sense as a regularizer, but in a security setting, a stochastic predictor can look stronger if we attack the wrong object. The deployed classifier is not a single deterministic circuit, it is an average over many masked circuits. So the attacker should not be forced to attack only one random mask. Our question is therefore not just, does dropout help? The harder question is, does it help when the attacker accounts for the dropout randomness? That is why the right side of this slide is adaptive. The real test is the random prediction rule that would actually be used. Here's the experimental object in one slide. On the left, the attacker perturbs a two-dimensional input with an infinity norm bound. The middle panel shows a small quantum neural network. The input is encoded, trainable rotations are applied, and a coupling gate connects the wires. Rotation dropout only masks trainable rotation angles. It does not remove the input encoding or the coupling gates. A mass rotation has effective angle 0 for that sample circuit. The stochastic classifier then averages predictions over several independent masks. For the attacker, this means a normal PGD gradient is not enough. The adaptive EOT PGD attack estimates the gradient of the expected loss over masks. This is a real essential protocol choice for evaluating stochastic defenses fairly. The study is intentionally small and controlled. We used two generated binary tasks, circle and moons, and two required quantum neural network families. The first is a one-qubit data re-uploading model. The second is a two-qubit variational classifier. We compare four training regimes: standard training, quantum dropout training, adversarial training, and adversarial training with dropout. The important comparison is not only dropout versus not dropout. It is whether dropout adds anything once the attacker and the training rule are both accounted for. The stochastic methods use Monte Carlo prediction with 16 masks. Adaptive attacks use 8 gradient masks per step. Everything is exact state CPU simulation, so we are judging the mechanism, not the hardware noise. This is the main empirical result. Each panel is one data set and model combination. The horizontal axis is robust accuracy at epsilon 0.1. The orange triangle is the combined method, adversarial training plus quantum dropout. The evaluated Monte Carlo prediction under adaptive EOT PGD in every required cell. That orange method is below adversarial training without dropout in mean robust accuracy. The drop is small for some cells, but the direction is consistent across the required matrix. The most visible failure is the circle task with the two-qubit variational classifier. There, adding dropout to adversarial training produces a large mean reduction. This is why the paper should not be framed as a successful new defense. It is a careful test, that rejects a tempting defense story. These slides state the central answer more bluntly. We begin with a plausible regularizer that is scientifically reasonable. Dropout can reduce overfitting in learning systems, and the quantum version removes select trainable rotations. But adversarial robustness is not the same as generalization. The deployed classifier is stochastic, so it must be tested as stochastic. We do that rotation. Dropout does not earn defense credit in a required setting. I want to stress that this is not a weak result. It prevents overclaiming. It says that for quantum machine learning, randomness should not be treated as protection unless the adaptive test also fails. Here, the adaptive test does not support that protection claim. The strongest story in our paper is about dropout combined with adversarial training. If dropout were a useful defense component, we might expect it to improve the adversarial training. It does not. This chart shows the pair difference between adversarial training with dropout and adversarial training alone. Negative means the dropout version is lower. All four means are negative. The largest is the circle variational classifier, where the mean difference is about minus 0.123. In that cell, none of the 5 seeds is higher for the dropout combination. That turns the negative result into a useful design lesson. Future work should not merely add stochastic masks after the fact. It should train directly for the adaptive stochastic object if robustness is the goal. We also ask whether the conclusion survives a separate transfer setting. Transfer attacks are not the governing white box result, but they are useful because they test whether a classically generated adversarial perturbation also harms the quantum models. The pattern is consistent with the adaptive results. When we compare adversarial training with dropout against adversarial training without dropout under transfer, the mean difference is negative in all 4 required cells. This does not prove that dropout can never help. It does show that our conclusion is not an artifact only of one white box attack construction. The same practical message comes back. Dropout is not adding reliable robustness beyond the simpler adversarial training baseline. The primary epsilon curve gives another view. This is the circle task with 1-qubit data re-uploading classifier. As epsilon grows, robust accuracy falls for every method, which is expected. At the central epsilon 0.10, the dropout stochastic method is below the standard deterministic baseline in this cell. Across the curve, the dropout lines track the baselines closely rather than opening a clear robustness advantage. This is important for how we write the paper. The result is not that one epsilon was unlucky. The primary curve suggests that stochastic dropout mechanism is not creating a robust margin in this controlled setting. It behaves more like a regularizer than a dependable defense. We also ran a 4-qubit confirmation check on the circle task. This was deliberately separated from the required study, so we do not claim scaling behavior. The dropout alone method is slightly above standard training in mean robust accuracy, but the interval crosses 0 and the effect is small. More important, the combined adversarial training plus dropout method remains below adversarial training alone in mean robust accuracy. So the optional check does not rescue the defense claim. It gives us a nuanced statement. There may be narrow cases where stochastic dropout alone gives a small improvement, but the overall evidence still does not support dropout as a reliable adversarial defense and still does not improve adversarial training. A fair stochastic test is also more expensive. A deterministic prediction costs 1 QNode evaluation per example. Monte Carlo dropout with 16 masks cost 16. Ordinary PGD20 plus deterministic evaluation cost 64 QNode calls per attacked example in our protocol. EOT PGD20 plus Monte Carlo prediction costs 352. That's a 5.5 times ratio. This matters because papers can make randomized defenses look attractive by using cheaper, weaker attacks. Our cost accounting says exactly what we pay to avoid that mistake. For the required experiment matrix, the total was about 16.1 million QNode executions, including the optional 4-qubit check. It was about 19.1 million. So the final takeaway is constructive. First, rotation dropout is not a reliable defense in the tested setting. Second, adversarial training is the more useful signal, especially for the variational classifier cells. Third, stochastic quantum defenses should be trained and tested against the rule that it's actually deployed. The future opportunity is not to abandon QML security, is to design defense-aware training objectives, better mask policies, and finite sampling studies that are clear from the beginning about adaptive attackers. That is why this is a positive negative result. We did not get a slogan saying dropout wins. We got a standard: do not credit randomized quantum classifiers until they pass an adaptive test. Thank you for your time. Please get in touch if you have any questions.